Welcome to Westech Direct's discussion of shell and precision investment casting. Foundry owners, casting engineers, even foundry buyers have lots of questions around shell. How to resolve shell defects, what are the differences in shell systems, and discussions around all sorts of materials, cobalt-based zircon materials, fused silica sizes, just dozens of complicated questions, or at least it seems complicated. But today we're going to talk to two really seasoned casting veterans, Eduardo Xavier and Jeff Kuntz. Eduardo has been a technical sales rep for over 2 decades at the highest level in precision investment casting, and he's extremely experienced in the shell process. And Jeff is also highly experienced as a technical sales rep, and he's run a foundry for decades, very hands-on. And I love today that we have a viewpoint from both the vendor side of things and the foundry side of things in precision investment casting. So gentlemen, welcome.
Thank you.
So today, I just want to make it clear to the viewers out there, we're talking about precision investment casting. This is not jewelry. This is foundry owners. We're looking at aerospace and commercial casting and automotive and medical. Our audience, generally speaking, should be foundry owners and PIC engineers, foundry management, and the buyers. And today, particularly, we're interested in the shell process, but we will talk a little bit about wax and other things that go on. They're all perfectly integrated together. But what I want to start with first, gentlemen, is let's talk about the overall process of a shell system. What is the basics of that for someone who's just entering, perhaps a new engineer? Eduardo, let's start with you.
Yeah. Precision investment castings is just like a very complex process to create a very precise casting that is not normally achieved by other means. You can reduce a lot of machining operations using this process to get very precise and final details to the produced parts.
Jeff, if you were going to give an overview of how that process worked, a high-level overview, how would you describe that quickly?
Well, the investment casting process typically starts with a primary, sometimes an intermediate, and then a secondary slurry. The primary is made mostly of fused silicas, zircon, different percentages based on what type of alloys, what type of maybe details you're dealing with. And the idea is to cover all the details and really replicate what you're trying to accomplish in the finish area. You want to be able to produce the exact details of the wax patterns. And for that, you need a primary that covers and creates a very nice, robust shell around that wax pattern. Beyond that, you want to be able to capture strength. So once again, the primary is going after the detail. It's covering every part of it. And then once again, in the backup, you're going to strength. You want to build coat after coat after coat to be able to withstand not only the investment portion of the process, but also the de-wax portion of the process. That becomes a critical part of it because it's got to be able to survive all the way through pouring. And there are a lot of things that influence the shell during this process. It could be the room itself, whether it's temperature and humidity, so environmental controls. It could be a de-wax situation where you were melting the wax out, and that expansion itself can create a number of hurdles. And then obviously when you get to the pouring area, you need to create a hollow shell that's strong enough to support the metal that's going into it.
And so if we take this at a really, really high level, a 30,000-foot viewpoint, essentially in lost wax casting, we're replicating a shape in metal. And we do that by making an extremely detailed wax model, wax replication of that, right? And then
Yes.
that we make a shell so that we can then therefore pour in metal and it replicates. But the problem being, it sounds like, is if I have something really big, I need an extremely strong shell. But if I have something very detailed, I need a shell that's going to be thin enough to match all those details, right?
Absolutely.
And so the problem may come in that some people don't have the proper strength. Some people aren't matching the details. Some people are introducing shell defects in the process, right? And so we'll talk a lot about like how do we resolve those defects. But before we get going, what are the materials? When you say like a shell system, what are materials that make up that shell system?
Okay. It is important to mention that all this process, you need to talk about time and temperature because first of all, you have a wax. Wax-based materials has a thermal expansion 600 times compared to the shelly materials. Any change on temperature, the wax will expand or contract much faster than the shell. all the shelled material, basically you normally use materials just like a Zircon on the prime, and different backup coats. You can use different materials, depends on your goals. This engineered shell system, there is being used for intermediate coats and the backup coats.
So explain that. Would a new investment casting engineer understand all of that?
Okay. The prime slurry, it is refractory materials that will contact with the metal. So this first coat cannot react with the metal you're pouring inside the mold. We call intermediate slurry for the slurry it is thinner viscosity and copy all the details of the first coat. And the backup coats is the coats that you can apply over the intermediate to give the strength and uniformity to the mold.
So when you're making something very precise, your first coat will be relatively thin but extremely detail oriented. Is that right?
Yes. It is thinner, and we call intermediate coats. We'll over this prime coat and continue copying all the details. And the backup coats will be increasing the shell thickness faster and uniform to produce a very strong and permeable shell.
What are the key materials that make up an engineered shell system?
I mean, I've already mentioned the primary, the secondary, and stuff like that. Obviously, the wax. And one thing I want to say is, the choices you make, it's really foundry specific. What type of equipment are we working with? Is it an automated shell system? Is it just a rotating tank? Is it, in some cases it's teardrop tank. How many tanks are we working with? Some people have maybe a couple different primaries, an intermediate, a backup. Some people just have a primary and backup. So, once again, it is very foundry specific. What are we dealing with? And based on that kind of drives what type of materials we're going to throw in it. I mean, some things are common. For example, the type of binder you use for the primary. It's typically a large particle binder, and then the flowers themselves can change. Sometimes people want to go with just a basic few silica-based slurries. Some people, because of reactive properties, want to go with more zircon, and some want that security of an all zircon. So it changes the flow of the slurry. It changes the reactive properties of the slurry. So once again, a lot of different things come into play when we're talking about what type of materials. The backup itself. I personally like fibrous materials in the backup. They're great for building around corners, hoop stress, really building a very nice, robust, strong shell system. But some people don't like the cost of that and want to go with something a little simpler, in which case, we need to modify that recipe to support that demand or prove that, that additional cost is a value that is going to support them, in the end.
So Eduardo, give me the fundamentals of a slurry. You guys have mentioned that a couple times. Tell me the basics of a slurry.
Okay, the components of each slurry is basically refractory particles as a solid part of the slurry and the liquid parts, which is the main component, the colloidal silica as the liquid part. You can add polymer on this part too, as an important part is the polymer, and you can add wet agent and any foam to this part, liquid part of the slurry. Each slurry has a different ratio between solids and liquids. You can translate this on the viscosity and how it flows and cover the mold. So that's why we have a 1' with the specific viscosity, refractory materials for the prime, different refractories and viscosity for the intermediate, as the same for backups too, different refractory and viscosity.
So on those refractories, tell me a little bit about some of the different types of refractories and why you might use them. And Jeff, let's go to you for this question.
Different refractories, you have both flour and you have stucco. Flour goes into the slurry and mixes with the binder. And then the stuccos themselves, you have a range of different mesh sizes, and that is kind of to support the slurry once the shell has been dipped. So to kind of back up a little bit, when the wax pattern is ready to be dipped, you plunge it into the slurry, you pull it out, and the idea is to manipulate the mold in a way that creates an even shell. an even slurry around the wax pattern. And then you will take a stucco, usually either in a fluidized bed or a rainfall sander, and it will completely coat the slurry. It will keep the slurry from moving around after it's been dipped, and it also creates volume. So you're creating a thicker shell as a result of it. And then so on and so forth. So it's very sequential, typically one primary coat, followed by a stucco. And then some people might have a second primary coat depending on what type of parts they're doing. And then it moves on to the next stage and then repeat. Once again, plunging the wax pattern into the shell, or into the slurry rather, and then adding another stucco coat. So once again, you're gaining volume. So the idea is to just have this order where you're creating a thicker coat until you get to a point where it's going to be able to withstand the process.
And so why, if I'm a casting engineer out there, why should I care about different brands of materials or different types of materials? Like, I get the size of the flower that I want and I'm done, right?
Fused silica is engineered, so once it hits the fired stage where you start melting out the wax and heating up the mold, it starts to transform into cristobalite. During this phase change, it actually gets stronger and stronger, and that becomes very important. So once again, the end game is to pour metal into that shell, and it needs to withstand the forces of the metal itself. So strength becomes very important.
So is it safe to say that different companies create different types of engineered particles, fused silica, et cetera, and then there are certainly different qualities of these refractories? Eduardo?
Yeah, so each material, you have a different supplier, different technologies for each material. Basically, for primes, normally they use a zircon flour on the prime, mixed sometimes with the fused silica. It will reduce the mold metal reaction using zircon on the prime. And then intermediate, you can use different materials for slurry and stuccos. You can use on the slurry aluminosilicate or fused silica as intermediate. As Jeff mentioned, you can apply a second coat of the prime, depends on each company. For backups, you can use fused silica, you can use aluminosilicate on slurry, not to mention as well as alumina too. Alumina is much high refractoriness for high temperatures. So depends on the metal you're pouring. You have a opportunity to use different refractory materials for each slurry as well.
And so as we go through this whole process, and probably the questions that all of the shell engineers out there who are more experienced are looking for are, how do we resolve the common defects? And before we jumped on this call, you guys gave me a list of some of the common defects that our engineers see all the time: inclusions, sand penetration, spalling, non-fill, finning, buckle, shell cracks, issues with delamination, how to get the slurry to stick to the shell. Let's address some of those. Tell me, either one of you, tell me about inclusions and some of the easiest way to address and to fix problems with inclusions.
If inclusions are a result of cracking, once again, so cracks will create fins. Those fins can get broken off during the pouring process, sending ceramic into areas of the shell itself. Some of them are subsurface, some of them are very obvious, but it does create a real issue for a lot of foundries. And then that goes back to really that deep dive into what is the reason why this shell is cracking. And that could be a number of things. It could be environmental factors. It could be maybe the wrong shell choice. It could be a drying issue, or even a de-wax where you're sending it through your autoclave or flash fire process. So once again, that becomes more of a knowledge of what their process is and what the potential issues could be.
How do they even start to troubleshoot that?
Well, that would take a person like Eduardo or myself, coming in with a new set of eyes and taking a look at their process.
Could they call you? Can they call West Tech Direct
Yeah.
and say help?
Yes, for sure.
Absolutely. I've worked in a foundry for 24 years. So yeah, no, I've seen it all. I've created it all in some cases, in my journeys. Yeah, that would not be a problem.
And just for the shameless plug here, you guys do have a shell room for R&D and validation type tasks, right?
Yes.
That is correct, yeah.
Okay.
Yes.
So inclusions are generally going to come from cracks. What are some of the key causes of cracks, and what are some of the things they should be looking at right off the bat before they call you?
Yeah,
Slurry health for one. So that leads back to West Tech maybe doing a slurry test, on their shell systems to see if they're healthy.
to monitor the room temperature, humidity, to see if the wax can expand or contract, and or even over drying, especially the prime, when they can have the problem of the shell cracking on the prime. This is the problem that Jeff mentioned about thinning, is because of normally over drying the prime and temperature excursion.
The wax will change size or may dry faster, and they have to correlate it by logging the data to see what's happening on what day and in what atmospheric conditions.
Absolutely. And a lot of times people don't realize that. And one thing we didn't talk about is over drying, on the primary. That can create some issues as well, leading to, thinning. So knowing exactly what your dry times are, and people sometimes have an idea of what they think they are, or they just come to work, with blinders on because this is what they've always done. So it's really nice to get, a graphical view of exactly what your dry times are.
Is that something they would do in the foundry, or is that something a lab like you guys would help with?
That's something we would do. You run into some foundries, some companies that have that capabilities, but for the most part, they don't. I mean, good for those that do have that ability, but once again, sometimes it's some outside eyes looking at the process and using these types of means to find out what potential issues are.
Oh, yes. Normally, we do a auditing on the process of the customer, because this kind of defects can come from different sources. It can come even from the wax itself, the quality of wax. It can create this crack as well. If you have a softening point of the wax will expand during the autoclave and can crack the shell. So normally we'll take just like an overview throughout the process to find the source of the cracks. It can come sometimes with the sum of effects, not only the, just like we were mentioning about the over drying, but can come from the wax, come from even the procedures during the autoclave too. It is important that we can help the customer to solve this kind of issues.
So it may not be that they have a bad shell. They might have an okay shell, but they might have wax that's causing a problem, or they may not have monitored the temperatures correctly. How many variables are there? Are there dozens of variables that can affect this?
There's a lot more than a dozen. Yeah, there are a lot. And kind of going back to Eduardo's comments, yeah, wax is a very important part of it. The thermal expansion, if you could have the best shell in the world, but if your wax expands beyond what that shell can hold, then you're going to have problems. So your wax very much has to complement the process.
So I know West Tech is about to announce a new gel set 2.0 wax. Actually, I think you guys have announced it, and it's just starting to hit the market. Why, for example, is that one going to have a different reaction with shell?
Usually when you take the filler out of the wax, you removing that one of those variables, that being the filler and what it's going to do through de-wax. Filler's got to, filler is very important. Sometimes it's to maintain dimensional, maybe cavitation. So a number of things. Some fillers flow really nice, but if there's a way to remove the filler, that another variable of the process, it's always going to be a good thing. And the gel set 2.0 seems to do very well dimensionally, cavitation wise. Wow. I mean, it's pretty neat stuff. And we've done a number of tests through DWAX. And because of that non-filled approach, we're seeing some very good results through the autoclave.
Eduardo?
Yes, another point is the filler during the autoclave process. It can clog all the pores of the shell and reduce the permeability during the autoclave, and can lead to the cracks as well. Just like Jeff mentioned, just like it is better to use just like the gel set 2.0 without filler. You can have a much better results on the autoclave.
Fillers can also settle a bit. So, when you're talking about a wax press, in your nozzles and your cylinders and stuff like that, that filler can actually cause some issues with the equipment, cause maintenance issues. So once again, removing filler is always good. And Eduardo mentioned the autoclave. Absolutely. I know people that have to scrape their autoclave and clean it regularly because of those materials falling out.
Mm.
So, once again, it's a cleaner process. That even includes residuals. And I know this is kind of going a little beyond, but when you're talking about fillers, de-wax, you typically, or you can have residual material that can be powder-like on the pouring cup itself. I'm yet to see a non-filled wax create any type of residual material. And that becomes really important, especially with reactive alloys. If that metal hits that powder, it is going to react in some fashion and create issues in your finish area.
GelSet 2.0 has no
Filler.
So would it be safe to say that a wax with no filler like GelSet 2.0 is generally less reactive?
I would say it doesn't have the filler in it that can be reactive because, once again, it's called lost wax because you're removing that portion of it. But kind of going back to the filler itself, it can leave a pretty decent amount of residue on your pouring cup. And if you're seeing it on your pouring cup, you can guarantee that material is also in your shell as well.
So,
and sometimes, when you introduce it to, a preheat situation, it becomes increasingly difficult, depending on the carbon, the amount of carbon to completely remove it. So if you're dealing with, let's say, a medical part that's got to be completely defect-free, aerospace as well, that becomes one more variable that a lot of people like to remove from the equation.
got it. So we had talked about a number of other defects, sand penetration and spalling and non-fill. Give our guys out there a way to resolve some more of these problems they might see, or at least ways to start troubleshooting.
Okay, first,
Eduardo.
let's talk about sand penetration. Normally, sand penetration, it means just like the stucco sand that you use on the prime penetrates to the layer of the slurry and had just like a sandpaper rough surface on the casting. This can be related to poor technique during the draining of the mold. It can be related to the variance of the viscosity of the prime as well. So first of all, you need to understand the composition as well of the slurry. One slurry with less polymer content, it will drain different, not very homogeneous around the mold. And the slurry deposition, as you don't have uniformity, some places on the part the sand will penetrate to this thin layer and can lead the kind of defect. So our goal is always look for homogeneous layer. Normally 50% by weight of each dip is slurry, 50% is stucco by weight. But you need to this occur uniformly, having a uniform coat each dip, especially on the prime.
So if I'm getting sand penetration, what are the first things that you would test or change right off the bat? What does the engineer need to do right then?
First thing, you need to check the viscosity of the slurry. You can check by using a piece of flat glass. You cover one side of the glass with the tape, then dipping in the slurry, drain, and put it on the rainfall sander to see if stucco is penetrating to the layer of the slurry. You remove the tape from the other side, and you can see through the glass if you have sand penetrating through the thin layer of the primer. It is a good test.
That's cool.
Jeff,
what were you going to say?
Want to add more?
I was going to say one of the biggest one of the biggest problems that foundries run into is sometimes it's 2 to 3 weeks later that you actually find out what the defect is. Let's say you finish the dipping portion of the process, and then it goes into it goes into a staging area for de-wax, another staging area for pouring, and then finally the finish area where you remove the shell and you actually have you actually able to see what the shell or what the patterns look like. So sometimes it's difficult to really kind of narrow down because once again, a lot of times it could be 2, 3 weeks ago, that you're trying to diagnose what could have happened.
Mm.
One thing that I really like in a shell room is people that actually have control charts and stuff like that. People monitor their viscosity. So kind of going back to Eduardo's comments, you actually have a chance to see what happened a few weeks ago when the parts were actually going through the process. That could also be humidity. That could be what I already mentioned, viscosity, but could be the shell room temperature. So there's a number of things that the shell room must monitor to kind of maintain a healthy environment for the shell process.
Yeah,
So I would,
I can imagine it's very expensive if you're 2, 3 weeks down the line and then you're just discovering the problem and you have to get this product out right delivered to the client. But also, like you said, nobody remembers exactly what was happening 2 or 3 weeks ago. So if you can't go back and look at all the specifications about what's happening, you could be in big trouble.
Yep, I've along those lines, I've developed control charts for a number of foundries. I did that back when I worked in a foundry as well, as a way to kind of use that crystal ball approach and look what kind of conditions were going on during that time.
Eduardo, you had a point?
yes, the key of this process is to have a very good process control. The process control, you can have the very good quality of the parts. So we're talking about quality of the process mainly. And it means just like we're talking always about the best practice. Best practice means if you are using a slurry, you have a very good procedures to prepare the slurry, to know when it's ready to be used and how to maintain, how to control all the evaporation of the water in the slurry, to have a very good stability on the viscosity and a very good control on the procedures. Not all the companies has automation for deep in area. Sometimes they're using hand dip lines. So we give training for the employees who is deep in the molds as well, to have a very consistent movement, precise movements, and all the employees will be able to have a uniform coding all the time, 24 hours a day.
Give me a tip on spalling or non-fill or buckle.
Yeah, non-fill. Yes, the main defects you can face in the process is number one, I believe, is inclusion. Second can be non-fill. You can have a lot of problems with the non-fill, shell crack, thinning.
So when I think of non-fill, I think of the permeability of the shell. Is that shell able to breathe? When you're pouring metal into it, that shell has got to be able to move air and gas through that shell in a way that that creates a very nice solid metal pattern. But then again, it could also be temperature related, whether it's mold temperature or whether it's metal temperature. You've got two different uh, processes that can be contradictory to what's best for the mold or for the pattern.
So where do we start troubleshooting on that, Eduardo? I take it that we're pouring the metal in here and there's places where the metal just doesn't want to go. And sometimes that's because your shell is not letting the gas permeate out, right? Sometimes it might be because of the shape. It could be because of temperatures. How do I start to fix that?
So we need to act as detectives on the process. First, we need to check, just like Jeff mentions, about pouring temperature and as well the fire temperature of the shell. You need to check this first. Second, you can have a cut on your shell to see how uniform is your shell. When you don't have a shell uniformity, you just like a finish section, the thermal characteristic of that part the metal can cool much faster on the thinner shell. And while it's cooling down on that part, the metal will freeze before feeling all the small details. So shell uniformity can be a key part of this process as well as permeability too. We need to work, just like I said, just like as the detective, to check all points in the process that can lead to this kind of defect.
So that's really interesting for me as a novice here. As the shell thins, as the metal comes in, it will cool faster. If it cools faster, it will literally harden and then not get to the places that it needs to get to.
Yes,
Yeah.
correct.
It's very
Fascinating.
possible. Yeah, absolutely.
Yeah.
And then
And
if the
just the
temperature oh, sorry, and if the temperature as it's going in is, say, slightly too low, you can have the same problem.
yeah, yeah,
Yes,
absolutely.
yes, as well.
Every time I think of, the pouring area, it's an orchestration. You've got three different factors. Well, actually, maybe four if you include the human factor, but you've got the oven temperature. What is the preheat temperature? What is the pouring temperature? And then you've got typically a transfer ladle to move the metal into a pouring area. So mold's got to come out of the oven in a way that's timely. As soon as you tap that metal and bring it over to that mold, everything has to come into play very quickly. And then the flow into the mold itself, that is, that's a delicate part of the process. Pour it in, without creating maybe air or trapped air in the molds. People that do this, time and time again, once again, it is very much just a very orchestrated event to bring everything into play. If you drop temperature, for example, when you're bringing that you're bringing that ladle over to the pouring line, wow, I mean, a 50-degree drop doesn't take long and can be the difference between a non-filled and a filled mold.
What is spalling, and how do we address that?
Spalling is when metal penetrates between two coats. So let's say you have your primary coat and your secondary coat, and you do not have a good transitional sand. So this goes back to the appropriate stuccos. And this is just one example. Sometimes that metal, let's say there's a crack or something like that, it will actually get into the primary and in between that primary and that secondary coat. It could leave a scab, a subsurface scab of ceramic as a result of it. It's really a very devastating problem to have. And to be able to get beyond it is very critical. It could be slurry health. It could be soak times. Am I creating a monolithic shell? So in other words, a shell that doesn't have variations from one coat to the next coat. That becomes very critical. And once again, that transitional sand really helps it. So kind of going back to the stucco, typically use a Zircon stucco for the primary. Let's say that's somewhere around 120 mesh. And then the transitional sand would be a 50 by 100 material. So kind of the next size up, and then in the back up, it would be a 35 by 50 material. There's different variations of the stucco sizes, but that's probably the most common. And once again, the idea is to build a very monolithic shell so you do not have that separation of coats, creating a potential where, metal can get into that process.
Eduardo, when you see spalling, what are some of the most common causes that you see, and how does my engineer out there, how do they fix that?
First of all, spalling is one of the worst defect the precision investment casting because it can come from all kind of different sources. It is the lack of adhesion of the second coat to the prime coat. Can be for example, room temperature excursions. While drying, the wax will shrink, and then you can separate the prime. Prime will follow the shrinkage of the wax and detach from the second coat. You can be as well, just like if you have a loose stucco over the prime, and then the second slurry adhere to this loose stucco, and then you don't have a good bonding between the second and the prime coat. So it is not an easy defect to be solved. It is a detective job, and we can help with this kind of defect. It is one of the worst, I can tell.
It sounds like there's actually a lot of detective jobs in figuring out these defects, because it seems that everything is so integrated and works with everything else. And I think that leads me to talk about Westech Direct's shell system as an entire system, as pieces that are designed to work together. Tell me when things work right. Tell me, for example, about Westech Direct's system and why the particles work together and why it's good to buy a system that's been made to work with itself.
Well, I mean, ideally, yeah, you want a system that complements, whether it be, a non-filled wax like the GelSet 2.0 you mentioned, or whether it's, the primary and the secondary. We recently launched, our engineered shell systems, our engineered flowers. And I got to say, from a guy that's been in a foundry for 24 years, they work really well. Now, with that in mind, the flowability of the material, the rheology of the material complements. So your detailed parts, I feel very comfortable dipping molds with, a large degree of details. Once again, having that read to kind of flow in those areas. It seems to be pretty robust. I've got it on an automated line. I've got it on a hand dip line, 2 hand dip lines, and, the human factor, which plays a big role. So automation, you're as good as your program. But when it comes to the human factor, now you're throwing a lot of different people into the mix. And it seems to create a very consistent shell regardless of the approach that's taken. It's also fibrous. So we've got a non-fibered and a fibered approach. I like the fibers, and I really like these fibers because I don't even know there's fibers in them. I've worked with a lot of fiber slurries, fiber enhanced slurries in my day, and I had to actually take some liquid slurry out and look at it closely to actually see the fibers, because the fibers can be a little bit clumsy on the flow of the slurry itself. But the nice thing about these fibers, they're doing exactly what they're supposed to. They are creating even coats around 90-degree angles, parts that typically are difficult, like elbows that have hoop stress. You see a lot of inconsistencies or weaknesses in those type of configurations, and it does a very nice job of creating an even coat around problem areas.
With the West Tech Direct engineered shell system.
That is correct, yes.
Eduardo, what about you? Tell me a little bit about how having this engineered system works. And I haven't heard you guys mention, Tech Coat and Tech Sol. How do those fit in the equation?
Yes, and we have a different, the Texol is our colloidal silica will be designed for each of these kind of flowers with fibers and without fibers to give enough strength as well, very good on uniformity of the shell. And we can design the engineer shell system depends on the goals of each customer. If they to produce uniform, faster, and easy, we can have all the solutions for the shell.
So if someone doesn't know exactly what they want, you can help them put together a set of materials that work from start to finish.
Yeah. And not only that, you mentioned earlier that, we have our own lab. We have our own shell room. So we are capable of R&D, proof of concepts, even, validating, a material that maybe we're trying to test against. So there's a number of things that we can do, once again, with the shell room. And then the lab itself, where we run MOR and we run permeability testing and full slurry testing, pH, gel, SiO2s, those kind of things.
So we've talked about a wide range of topics. We've talked about the materials. We've talked about the process. I feel like we could have hours and hours and hours of this discussion, but we've just touched on everything. It sounds like the easiest way for someone who didn't get their answer in this is to call West Tech Direct and ask for one of you guys and say, I need help. And you guys can either talk them through some of the problems or give them some tests to be doing. I saw a presentation that you had made earlier, Eduardo, where you have some drawing best practices and you have a really cool an example of a drawing study to show how things actually dry and what the patterns are in a chart basis. So if they didn't get the answer they needed, go ahead and reach out to you guys. And you can also help put together programs and materials lists. And you guys also send out samples. Is that correct?
Yes, we send out samples. That could be wax, that could be shell related. So it just takes a brief conversation to kind of understand what our goals are.
Eduardo, did you have more to add to that?
Yes, yes. So first of all, we need to, just like Jeff mentioned, what are your goals? We ask the customer. So we have a program that we can do just like a audit on their process to identify points of the improvement. We can create a lot of different projects, and then we start applying this each project. We give them priorities for each one. We have the program for improving process on the customer based on their goals.
Before I wrap up here, my notes had a note here about permeability, and then you just mentioned the lab. Help me understand about permeability testing and MOR.
MOR testing, modulus of rupture, that is used to determine green strength and fired strength, or hot strength in this case. Basically, the green strength is what type of strength values are we seeing through the investment portion and into DWACs. And then the hot strength is what are we seeing after the molds have been heated up to, let's say, 1800 degrees, for example. And that becomes increasingly important because whatever that strength value is, that is what the molds are going to be receiving, when you start pouring the metal into them. So having good values, on both accounts is very important. And not only that, the knowledge of that is very important going into a situation. So we call it baseline data. What exactly are we dealing with right now? And some cases, if you got high values and you're having defects, maybe we need to look in other directions. And then permeability testing is very important because your molds have to breathe. So they have to be able to survive the DWACs. They have to be able to breathe enough so we don't have some of the misruns or maybe other types of defects, because that air, that gas needs to permeate through that shell. And once again, having that data, that baseline data, understand what we're looking at, becomes very important. And that actually goes all the way back to the shell system itself. There's lots of things we can do to the shell system to improve permeability, but the knowledge is the key part of it. Do we need to look at it? If so, what is going to be the next step? And kind of going back to our lab itself, where we have a shell room, now we're able to test those in a lab environment before we introduce a new shell system.
So tell me how that happens. I have my own set of materials and I call you with a problem. Do I send you a batch of my materials and what I'm using? Like how does the process happen?
Yeah, that's exactly it. You would call and you would say, "Hey, I've got whatever the issues may be." Understanding what we're dealing with first is very important. So that could be a slurry test. We're testing SiO2s, we're testing gel, we're testing pH, and then going back to, the perm and the MOR, that we have our own kits that we send out. They are specific to the equipment that we have. So we don't want just kind of random stuff. We want that standardized approach for testing. So we would send them to you with a set of instructions. And then, once complete, you would send it back to our lab and do the rest.
Eduardo, anything to add on permeability or MOR testing?
Yes. So this test is used, for example, to reproduce the current situation of the process at the customer site. And we have specific data as a starting point. And after we running our trials with our engineer shell system, we run the same similar tests exactly, and then we can compare where the current situation and where you're moving the new situation at the desired state for the customers. We work with the data. That's the most important part of thing.
I love all that. So thank you guys so much for being here. I probably kept you too long, but I realized, like I said, we could talk about this forever. This was a quick dive into shell systems and troubleshooting in precision investment casting. There's lots more information on westtechdirect.com, or you can just call and talk to the experts there. Stay tuned for our next conversation. If you guys go ahead and like and subscribe on YouTube, if you're here, you'll make sure to see the next video that comes up. And as I mentioned, if you have any wax questions, call them directly at 951-279-4496 or visit Westtech Direct, WESTECH direct.com. Until next time, keep casting.
Thank you.